for stocks, you can build algorithms based on that, 55, 60 maximum. I've never heard of anything higher than that, maybe.
This percentage you're talking about, 55, is that
Accuracy.
predictive?
Yes.
I mean,
How accurate could it be in predicting that stock's performance? Yeah.
But with that, you can make money, as long as it's over 50.
it's a random poll.
Yes, but there's a 40% chance you lose it too. So, yeah, of course. Yeah.
You don't do that more than once.
Kind of. Oh, so you have to spread. But it's not as high as facial recognition, for example. 98, 99%. Okay.
Let's see. Ahmad, you talked about the Twitter feed. What was Microsoft Bob? Was that AI?
No, they gave it wrong data.
What's that?
Well-
No, I'm talking about the paperclip that Microsoft used to have embedded in
Oh, I
Windows
don't know.
98 or whatever it was. Was that AI? I'm trying to figure
Oh, you
out.
mean the clip that says, "I noticed you have a problem"? or-
Yeah, exactly. Was that AI or was that something else?
I mean, I'm not saying I'm the gatekeeper for artificial intelligence definitions. These are loose terms. No, I wouldn't say. I'll look at it in AI. Let's say you log into a website. We implement this for one of the banks. You log into a website and you have questions about your checking account. You communicate, you chat with a module, and it basically tries to pick up the verbs and adjectives, and based on that says, oh, this guy wants to know something about checking account information, an FAQ.
Right.
Basically try to minimize the number of people who's going to call customer service. So through the conversational chatbot, that is a typical case of an AI. Basically try to see what kind of data can I give you that's static, web pages, instead of having you talk to an actual customer service representative.
Gotcha.
Yeah,
So far, you talked about labeled and unlabeled data.
yeah.
But once you have an unlabeled piece of data and you make a classification decision, does that get incorporated into what you consider your reference set of data for making future decisions? Is that
It can be based on the project, and then we'll have to talk about the process and agile versus waterfall. But it can be, depending on the client. There's no set rule for that. If you want to increase the accuracy, but that means that algorithm is going to stop being in production and go back to being in development.
Can we, for instance, develop different engines, artificial intelligence, that they have different data, labeled data, and then kind of they teach each other. They learn from each other, and data becoming more purified while this time is going and more data is coming.
Are they the same engine?
No, they
Are
are
they clones of each other?
separate engines. But they are
So they have separate classifiers? Separate.
exactly.
Okay, repeat the question. So we have training data.
Yeah, like you have this separate classifications, but the same subjects that you, for instance, you are using right now, the stones, right?
Yeah.
And the rocks. Let's say you have a couple of engines, but they're based on different classifications. So the margin of error is kind of during the time as you collecting more data, they are kind of teaching each other, and then it's purifying more and more, and becoming the error less and less.
Is it the same training data?
Yes, it's the same. It's the same subjects that you. So let's say it's the same stones that
Yes.
you bring from the Mars.
But what do you mean by training each other?
In a way, like because one engine using these features, another engine using another features.
So basically this engine has only two features.
Yeah,
I was going to come back. This classifier has only two features. Real world classifiers have hundreds and thousands of features. So in your scenario, you would have both of them, merge them together, make it one engine. Because real world examples, I was going to get to it a little bit later, they have multiple classifiers working together. But calling them independent separate engines, I don't know, I mean, obviously you can do whatever you want, but it doesn't make sense architecturally. You can have one algorithm which has multiple, okay, let me talk with the slides,
Okay.
because I have to explain some terms and then we can continue.
okay.
So, as you guys remember from the scatter plot, we divided the space using dividers, and we have decision space and decision boundaries. Remember those terms, decision boundaries. This can be called a decision tree, the thing that we've done. It can be represented via code, like this. If granularity is less than 12.5, then if density is less than 0.9, it's a volcanic, definitely. Else it's plutonic. There's another else at line number 7. If granularity is above 12.5, jump to that the number 7 and go to Platonic. It's a Platonic Quran. This is a very simplified case of a decision tree. If-else statements. Now, the important thing about, this is where the magic of the engineer comes in AI. In machine learning algorithms that use decision trees and classifying decision trees, you have to be very careful what features to choose on. Granularity and density. The scenario I gave is very simple, but in real world scenarios, you'll have hundreds of features to choose from. Which ones are the important ones? That's why you have to interview a lot with the client to find out what is the topic. And at what points you should divide up, at 12.5, at 0.9, because that's very important. And again, decision trees is just one basic example of machine learning techniques. There's hundreds of algorithms in machine learning. More and more being published. There are different non-linear lines that can go through the decision tree. For example, in my scenario, it was a straight line. That means it's a linear function. X equals y plus 2 or something. You can have curvy ones. You can get mathematical with it and get funky polynomials. Some of them will have multiple decision trees, which people would call forests, because it has multiple trees in it. So some classifiers would have more than one decision tree, like you were talking about, and that would be called a forest. Still, it would run against the same label data or training data. Now, there are other non-tree approaches to machine learning. So that when you come out of it, you realize there's different ways of doing it. But think about, again, we're slicing up the decision space using arbitrary lines. And machine learning, the algorithm, the classifier, it's its own job to find the best way to maximize correctness while minimizing errors. So there don't have to be straight lines. You can have polynomials or very, very funky mathematical notations. The formula for it is very complex to come up with. That's what the machine learning algorithm is doing. Finding for this specific decision space and boundary, how can I slice through it and get the most? So, for example, for the Martian geology, I only use 2 features, which is really easy enough for humans, mere mortals like me and you, to visualize. But let's say I want to make it a little bit more funky. Let's say I want to add another feature, make it 3 features. Let's say I want to add viscosity. You have to imagine the 2D lines, the x, y, is going to become a 3D plane. Because it's going to be x, y, and z now. So it's going to become 3D. And I'm going to have to create decision boundaries in 3 dimensions. That line is going to go 1 dimension, it can become 3-dimensional. And they don't have to be straight either. They can be polynomial, they can be curvy, it can be some weird mathematical notation. But even with this weirdness or the way it's getting funky, this is not even a basic example, this is way preliminary. Real world scenarios would have hundreds and thousands of features. At Google and Amazon and Facebook, that's what they're working with all the time. So you can agree this is getting too hard to do by hand or by just eyeballing it. So there's no good way to visualize, honestly, 4 features or 5 features or figuring out, an equation for a hyperplane rippling through 1,000 dimensions and try to classify them. There's no way of doing that. But computers with clever machine learning algorithms do that, and they do it all the time at Google and Facebook. Any questions so far? We're cool? Okay. Now, if you look at all of what we talked about, most of it was talking about numbers. And in reality, decision trees and those techniques are basically statistics. I've got to do computer science. Machine learning is basically a statistics rule. It was being used way before computers existed. There's nothing new here. What's new is that they just got juiced up on computers. Computers have the capacity to perform stable set tasks. But decision trees have existed in statistical literature probably since the 1900s, or like the 19th century, I'm sorry. And statistics has always dealt with making confident decision using data. So this major approach was rooted in statistics. Now we're going to go to another approach for AI, which has nothing to do with statistics. Artificial neural networks. Artificial neural networks were inspired by neurons in our brains. I'm not a biologist, but the way the neurons work, the way I was able to look it up, is that you have cells that transmit chemical and electrical messages. A neuron accepts multiple inputs from different cells, processes them, and emits its own signal. And you have a huge interconnected network of neurons. Each neuron is doing a very specific, weird, stupid task. They didn't understand what is it. But on a high level, the network itself can capture abstract ideas and process complex information. So these interconnected networks are the ones that are processing. Kind of like you know, your brain, guys, when you're watching me now talk. How you're processing information. So, there's a concept in technology called biomimicry. You try to design systems based on biology or based on evolution, how Mother Nature has designed them. So artificial neurons are very familiar. But instead of taking chemistry, chemical, electrical inputs, they take a number in, or multiple numbers in, and they spit a number out. And they get organized into layers. They are connected between them with links, and they create a network of neurons. Hence, neural networks, the name, artificial neural networks. So now, let's go back to our Martian geology and rock example. Let's see how we might be able to do it through artificial neural networks. Now, in here we see, we see three layers. Input layer, hidden layer, output layer. Input layer is where we have the features, so granularity and density. This is where we're testing a specific unlabeled data. So this is one rock that has granularity of 13 and a density of 0.76. That's a number that's going to go into the hidden layer, which has the neurons that we're working with. And the neuron is going to process the number and spit out another number. We're going to have two outputs at the output layer, a volcanic or plutonic. The most excited neuron, excited means the one that is the answer, is what the network thinks this classification is. Now, again, neural networks are very, very complex. There's a lot of mathematics involved here. The process, those arrows that go from one neuron to another, each one of them has its own mathematical function. And in the hidden layer, there's mathematics that gets involved too. I didn't want to display it because I don't want to get down into the technical aspect of it. All you need to know is the magic of your work is knowing how to set these variables correctly, how to tweak them properly. When you first establish a neural network, all those numbers are random. So let's say, for example, at the hidden layer, we say x equals, like, you know, the function of any hidden layer is to make any input x multiplied by 2 and divided by z. All of those are going to be random. So at the beginning, it's not going to work at all. But we have labeled data and training data. So we use training data knowing that I'm going to give it a plutonic rock, and you have another algorithm that goes in and starts tweaking the values for x and z until it starts pushing the neural network gradually, slowly, gradually, over multiple iterations to the right answer. Does that make clear? Does that make sense to you guys or no? You know, I want to make sure this is sinks in. So the parameters that are going to be given to the green dots are set up to random. There's no logic behind them. You'll have, well, there's be logic about the structure of the formula. Is it going to be 2x plus y? Is it going to be derivative or something like this? But it's all random. And then an algorithm goes in using training data and reconfigures and tweaks it slowly again and again and again. But when you first establish a neural network, it's all random.
So what do the green dots really do?
These are the neurons that process the information and make a decision. Each green dot would say if granularity is 13 and density is 0.76, it's going to process the number and spit out another number. Okay, let's put it this way. So we know this is a rock. It has 13 granularity of 13, density of 0.76. It's going to be either plutonic or volcanic. Those numbers are going to go into the green dots. They're going to process that number, either add, subtract, divide, do something to it, and then the number is going to come and they're going to output that number into either this node or that, into both nodes. But the node with the highest number is basically the answer, the way the neural network thinks it is. But in the beginning, it will be very random. There will be no logic behind it. In the beginning of neural network, you have to train it. The same way you train a child. Slowly, he doesn't know how to walk. He has to go again and again and slowly learn it. The analogy here is that the algorithm that you built will go in and start tweaking those values that we used for the green dots to make it go for plutonic or for volcanic. Make sense or no?
Is the analogy like, I was once told that there's like multiple paths, like hundreds of possible paths. But then once you give it the training data, it sees which paths produce the correct answer according to the training data, and it strengthens those paths, and those paths become the stronger paths that are more favored.
If it has.
Well, yes, I mean, this has multiple paths. This has plutonic and volcanic in the beginning. But there should be one answer, essentially.
Right.
So yes, it's slowly nudging it. Let's say this scenario, because it's 13, it's above 12.5. Remember in our decision tree, If it's less 12.5, it's something, and if it's above, it's something else. So this is very clear. 13 is plutonic. So in the beginning, it'll be random, plutonic, volcanic. It's gonna, the numbers here is gonna give you 5 and 6 and 4 and 8, and you're never gonna, but slowly, one of them should be like 0 or like 0.5, another one should be like 12.
When you say numbers, what do you mean by numbers on the output layer?
So eventually eventually the output layer should have a number on it.
Like what?
Some number, some
0
integer.
to 1 or?
That depends on the algorithm. Some people would say the algorithm should load it between -1 to +1. These are all big decisions that you make as an architect of the AI engine. But it's going to be a number, an integer or some other version. It could be a real number, but it's going to be a number. It's going to be, okay, 1 and this is 9. That means very clear that it's volcanic and it's very confident in it. That's after it was trained. In the beginning, it might be 4 and 5. It might be 2300 and 2400. But slowly, you want to guide it towards the right answer. And that's when it starts nudging and tweaking the parameters that get involved in the hidden layer, and it'll move it towards the right answer.
And you mentioned confidence, because that is, oftentimes it'll issue a quote-unquote answer, but also a confidence number out
Yes,
of the answer
yes.
as well.
That's the accuracy that I will talk about, 85% accuracy. So here, for example, facial recognition is a clear case of neural networks. Come up to 98%, 99%. I mean, Google and what is it, Facebook, in 2015, their algorithms were doing 98%, 99%. Facial detection, not recognition. Detection means I see a face, I don't know who's the person. There's no, security, but I know there's human faces here. Yeah.
But for any given person, you take the thing and say, is that a person? Yes, it is, but I'm 40% accurate. So it's not that sure. Or, yes, it is, and I'm 90%
Well,
accurate.
it's 99% for Google and Facebook, the algorithm, for face detection.
But overall, it's 90%. But for any one given test.
No, that means any image that has a picture in it,
Yeah.
and a human face in it,
Yeah.
it's 99% sure that's going to be picked up. Yeah,
Oh,
that's what how you interpret.
okay.
I mean, computer vision is a little bit specific. Okay, we do computer vision too. In computer vision, the picture shouldn't have a lot of contrast. That means if it's a dark night and you don't see your face is not illuminated, it might not pick it up. But if it's a clear face picture, yes.
But like when I use voice recognition,
Yes.
like some engines for that, and if I say,
SDK, naturally speaking, Dragonfly, which one?
right now I'm using one called Vocapia, which is from France, but
Okay.
and it comes back where, and also I use sometimes the Google one or the one that comes with various ones. Anyway. The ones that come standard with the
Anyway, okay.
iPhone. But anyway,
Siri.
yeah, with the developer one. Anyway, if I say Mary had a little lamb, and it writes Mary had a little lamb, it'll say Mary. I think you said Mary. I'm like 80% sure. Had. I'm 40% sure you said had. You know what I mean? For each individual point of data, it gives me a different confidence level.
But you're comparing apples and oranges. Those data, this is text, voice data. This is separate from, so that's why AI is very context specific. So voice data is different than pictures.
Oh, I realize.
Yeah, but okay, that's true. So the confidence interval, so when it's 40% for lamb or whatever,
I mean, for any given thing I said, it's like I think you said this word, but I'm only, it has a certain confidence for each data point. Is what I'm saying, not overall.
I'm sorry, we have a question.
So I have a question on the input layer. That's where you're feeding in the training data. And
This is the unlabeled data.
the unlabeled
Yes.
training data.
It's not training data.
It's
It's
not
the
training
data this is when the robot goes back to Mars. Well, depending on what scenario we're talking about. If you're training it, this is training data, but in this scenario, this should, once the algorithm is
Okay,
live,
depends on what right, it's training or you're actually using.
Yeah.
But my question is, where you're showing 13 and 0.76,
yes.
that's very specific. Could you explain that?
So those are the two features we talked about. You remember the features when you said when the geologists went to Mars, they said we're gonna pick up a rock. I know it's plutonic, but each rock we're gonna identify it by either granularity or density. Meaning, let me go back to the scatter plot.
You're showing it as inputs.
Yes, I am showing this, but yeah, because so let me go back to the scatter
It's for
plot.
a specific rock, but they say now you pick up this rock kind of faster.
So this was the same thing. I'm showing these are. This is a rock. This is 12.5 probably, and 0.2. This point here. I'm just doing it in a different way. That's what neural networks are different. But basically, this scatter plot is showing 200 rocks that are labeled. So I know the blue ones are definitely plutonic. The red ones are volcanic. But I have to show each one of them represents.
I was thinking you were showing it in the training mode. I guess you're not.
It can be used for training too. Yes. Let me.
When you're using in training, you're feeding data. and
Yes,
not-
let's
not-
assume it's training for that purpose. If it's training, let's go with that approach. So yes, but I'm providing features. So imagine if it's a real live algorithm, it's going to have thousands of input neurons. But let's say for training, because as you guys remember, in training, the values given to the green layer, the hidden layer, are random. So it's going to be maybe 5% sure about which neuron is going to come out from. So there's another algorithm that comes in and monitors this performance and says, okay, this is wrong. I know that what I gave you is lab. It should be higher than 40%. So it retweaks the algorithm again and again. And this is very complicated. That's where I try to abstract it. But it goes over it again and again and again. Now this is a very memory intensive and computing intensive. But basically slowly we're pushing and nudging the algorithm or the neural network through tweaking the parameters in this green layer so that it can make another output, move the output in a different direction. In this case, let's say it should be volcanic. Go ahead.
And so you're saying that during the training process, there's human interaction tweaking the hidden layer?
There's an algorithm that's built by a human
Okay.
that tweaks the hidden layer, yes. It tweaks the parameters, the way the hidden layer processes the data. Yes.
But also in the case of voice recognition, there's Mary had a little lamb, and if you go back and correct it, that, no, I didn't say Mary had a little lamb, Mary had a little ham, you know, then that goes back into the hidden layer to tweak the algorithm.
So that's not true. I mean,
No.
we shouldn't mix voice detection is different. Voice detection, you have to look at you know when you have a stereo, you have to equalizer, that thing. For English speaking, the equalizer, I mean, I can make it, but that's a separate field of AI. That's why AI is specific. You know, in the equalizer, they built ranges for vowels and consonants. So E, U. So it picks it up and says, okay, this is an E, this is an A, this is an O. And for English speakers, for example, we'll have a knowledge bank for language. So if I say Mary was, most probably the next word is going to be an adjective. So if you give it an adjective versus a verb, because of the knowledge bank. So it's a little bit different, not necessarily like neural networks. So again, guys, AI is a broad term. Each field gets implemented differently. Computer vision, and some of them use neural networks, but computer vision uses it differently. And voice to text is a little bit different.
Right.
Yeah.
So in your diagram, is it significant there were 3 green nodes?
No,
Could
no.
you pick, could have
No,
been 2
you-
green nodes, it could have been 1.
You need a lot of neurons. You need a lot of nodes.